In this video, we will discuss the OC1 algorithm, which is used to perform classification with oblique decision trees. Decision trees are a central method of experimental machine learning and are used as data classifiers. Many decision tree algorithms exist for data classification. Some common examples include CART and ID3. The left figure here shows the structure of a decision tree used for numeric attributes. The right figure visualizes the result of classification on a dataset with the left decision tree. There are two types of decision trees to consider for classification: an axis parallel decision tree and an oblique decision tree. An axis parallel decision tree takes a single attribute into account in each node. The hyperplane at the split can then only be used at a right angle to the axes. Only using axis parallel splits comes with some disadvantages. When data points are not univariately separable, it becomes more difficult to make an accurate classifier because it requires more splits. This leads to larger and more complex trees as well as slower classifications. This top figure shows all the parallel splits that would need to occur in order to classify an example dataset. In contrast, an oblique decision tree method like OC1 tests a linear combination of real attributes at each internal node to make a decision split. When tests are performed with this method, they create hyperplanes at an oblique orientation to the axes. This leads to simpler decision trees. This bottom figure shows the oblique splits for classifying the example dataset. As we've previously mentioned, a hyperplane is used to split data points from a given set. We define a hyperplane as a vector of real values and label it H. This vector contains weights that correspond to each of a given example's attributes. It also includes a bias HD plus 1, which anchors the hyperplane's normal line. When we take the dot product of our plane H and a point P, we get the equation on the bottom left. The sign of this dot product then determines a split. A split where all of the points result in a dot product with the same sign is referred to as pure. The impurity measure used in this algorithm is a metric to calculate how many misclassifications are caused by a given split. A lower impurity measurement indicates a better classification. This is important to note because the goal of OC1 is to minimize the impurity at each node of the decision tree. We consider it a greedy algorithm for this reason.
The OC1 algorithm begins by finding the best axes parallel split. As explained soon, this is done by perturbing each possible axes parallel hyperplanes until a minimal impurity hyperplane is found. Assuming we have found such a plane, we search for a less impure hyperplane by perturbing each of the coefficients of that hyperplane. In other words, we adjust or perturb each of the coefficients defining the hyperplane to minimize the impurity. This perturbation algorithm optimizes a single coefficient of the hyperplane on the training set, a so-called best univariate split. To do so, it solves for the coefficient when the hyperplane goes through a data point. In other words, the dot product equals 0. It finds all these coefficients for the hyperplane going through all the points in the training set. This in effect projects the points onto a one-dimensional space. We then sort the coefficients representing the points in this univariate space, sorting effectively new hyperplanes in order. If we find the midpoints for each successive coefficient for the sorted coefficients, we obtain t-1 hyperplanes separating each of the data points. After that, we examine each of these hyperplanes for the best, least impure split. In effect, the perturbation searching process amounts to a sweeping through the data points for the best split. This perturbation process of coefficient comes in different flavors. For example, the perturbation of the coefficients could be done until coefficients no longer change. If the potentially improved hyperplane is less impure than our best so far, we update it. This amounts to the so-called first step of OC1. At this point in time, the search has fell into a local optima, as we found the best coefficients as we can. So to help escape that, we generate a random vector and add it to the best hyperplane times a variable coefficient alpha. This alpha coefficient will be optimized through the perturbation algorithm to find the best new hyperplane using the best univariate split with alpha. This perturbation algorithm optimizes the alpha for adding the random vector onto the hyperplane. Fortunately, solving for this alpha is trivial to find a new hyperplane going through each of the data points. This again projects the data onto a univariate space. And again, we sort these coefficients, sorting their representative hyperplanes. We find the midpoint hyperplane separating t data points by finding the t-1 hyperplanes with the midpoint alphas. Again, we find the best split made by these hyperplanes. In effect, this perturbation searching process makes a pivotal sweeping motion through the data points.
Adding this random vector and the augmentation of alpha amounts to the second step of OC2. This local optima escaping process is repeated up to some j number of times. Each time this is done, if the result of the perturbation yields a better split, the algorithm goes back to step 1 to optimize those coefficients again. After the search is exhausted and can no longer improve the coefficient, we start the process all over again, except with a random hyperplane. This process is restarted up to a user-specified R time, similar to J. After the R iterations, OC1 amounts to finding a very good but maybe not the best split at a node in a decision tree. The OC1 algorithm is a recursive decision tree builder. After it finds the best split at one node, starting with its root, it will recurse on the left split data and on the right split data. Not shown is the case in which the data points are pure with a single classification and the recursion immediately ends. A decision tree for classification is generated as a result of running OC1.